48 hours from now, something impossible reaches Earth. 3I Atlas, an interstellar visitor, exhibits what astronomers are quietly calling the 14th anomaly. Two jets, perfectly aligned, both pointing at the sun. The odds of this happening naturally? 1 in 40,000, about the same as flipping heads 15 times in a row. Meanwhile, the United Nations just launched the largest planetary defense drill in history. Coincidence? Maybe. But here's what keeps scientists awake at night. This object's trajectory threads through Jupiter's gravity well with surgical precision. Its composition defies everything we know about comets. And in 2 days, we get our only chance to observe it closely before it vanishes forever. December 19th might be the day that reframes everything we thought you knew about whether we're alone. You'll want to stay close as 3I Atlas draws near. Hit subscribe and stick with us so you're here when Atlas reveals what it really is in the next 48 hours. The cosmos keeps its secrets close, but we're about to uncover them together. The clock is ticking. In 2 days, something ancient and alien will sweep past Earth at a distance of roughly 1.8 astronomical units. That's about 270 million kilometers if you're counting. You might think that sounds safe, and you'd be right. But safety isn't what has astronomers around the world glued to their telescopes right now. Fingers trembling over keyboards, voices hushed in conference calls that stretch across time zones. What has them worried, excited, terrified even, is what this object might actually be. 3I Atlas. That's its official designation. The third confirmed interstellar visitor we've ever detected. The first was Oumuamua, back in 2017. That strange cigar-shaped thing that sparked 1,000 debates and made a Harvard professor stake his reputation on the possibility of alien technology. The second was Borisov in 2019, which behaved like a normal comet and calmed everyone down. And now we have this one. This visitor that doesn't seem to have read the rulebook. An astronomical unit, by the way, is just the distance from Earth to the Sun. About 150 million kilometers, give or take. Scientists use it because saying 270 million kilometers gets tedious when you're dealing with cosmic distances all day. So 1.8 astronomical units means this object will pass us at roughly 1.5 times the distance between our planet and our star. Close enough to study, far enough to sleep at night, supposedly. Here's where things get interesting. Recent observations have revealed something that shouldn't exist. An anti-tail. Picture a comet in your mind right now. You're probably imagining that classic image, right? A bright head with a glowing tail streaming behind it as it races through space, blown backward by solar wind and radiation pressure. The tail always points away from the sun. Always. It's one of those iron laws of cometary physics, as reliable as gravity itself. Except 3I Atlas didn't get the memo. Observers have documented a tail structure pointing toward the sun, not away from it, toward it, as if someone installed the thing backward, or as if the normal rules simply don't apply here. The amateur astronomy community went wild when this news broke. Forums exploded with speculation. Social media lit up with claims about math anomalies and perfect jets, and probabilities so unlikely they bordered on impossible. The professionals, meanwhile, maintained their characteristic caution, speaking in measured tones about unusual features requiring further study, and phenomena not immediately explained by conventional models. That gulf between excitement and restraint, between wild speculation and scientific rigor, is where we find ourselves right now, in the gap between what we want to believe and what we can prove. But there's one claim that stands out from all the noise. One calculation that refuses to be dismissed, no matter how many times the experts try to wave it away with talk of selection bias and observation angles. They're calling it the 14th anomaly. Two jets, perfectly aligned, both pointing directly at the sun. not approximately toward the sun. Not sort of in that general direction. Perfectly aligned. The person who ran the numbers claims the probability of this happening by pure random chance is roughly 1 in 40,000. 1 in 40,000. To put that in perspective, those are roughly the same odds as flipping a coin and getting heads 15 times in a row. Could it happen? Sure, anything's possible. But would you bet your house on it? This is where the scientific community fractures into camps. On one side, you have the pragmatists who point out that comets do weird things, that observation angles can be deceiving, that we're viewing a three-dimensional object through a two-dimensional lens and making assumptions that might not hold up under scrutiny. On the other side, you have the ones who can't shake the feeling that something isn't adding up, who lie awake at night, running the calculations again and again, who wonder if maybe, just maybe, we're witnessing something that will rewrite every textbook. The official narrative remains calm. 3I Atlas is a comet. An unusual one, certainly. An interstellar traveler that formed around a distant star and got kicked loose by some gravitational interaction we'll never witness. It's made of ice and rock and organic compounds, just like comets born in our own solar system. It outgasses as the sun heats its surface, creating those jets and tails we observe. Nothing to see here. Move along. But the unofficial narrative, the one whispered in chat rooms and shouted on conspiracy channels, tells a different story. This narrative speaks of impossible physics and hidden purposes. It asks questions that make tenure-track professors uncomfortable. It connects dots that might not want to be connected, and it points to one unavoidable fact. In 48 hours, 3I Atlas will make its closest approach to Earth, and we will have our best and perhaps only chance to observe this object in detail before it vanishes back into the cosmic dark, carrying its secrets with it. So what are you about to witness in the next hour? We're going to explore both sides of this mystery. The measured scientific interpretation that sees a strange but natural object, and the speculative discourse that sees something far more unsettling. We'll examine the data, dissect the anomalies, and let you draw your own conclusions. Because by the time we're done, you'll have all the information you need to decide for yourself whether 3I Atlas is just an unusual comet that happened to wander into our neighborhood, or whether December 19th, 2025 will be remembered as the day everything changed. The day we finally had to confront the question we've been asking since we first looked up at the stars and wondered if anyone was looking back. Let's talk about probability. Not the boring kind you half remember from high school math class, but the kind that makes scientists lose sleep and stake their reputations on interpretations that could make them look foolish or prescient, depending on how history judges them. The 14th anomaly isn't just a catchy name someone pulled from thin air. It represents a specific, calculated claim about the behavior of 3I Atlas that, if accurate, pushes the boundaries of what we can reasonably attribute to natural processes. Two jets, both pointing toward the sun, both perfectly aligned. The calculation suggests roughly one chance in 40,000 of this configuration, arising by random chance in a natural comet. To understand why this matters, we need to understand what jets actually are in the context of cometary science. When a comet approaches a star, solar radiation heats its surface. Ices sublimate, going directly from solid to gas without bothering with the liquid phase. This escaping gas carries dust particles with it, creating visible jets that stream away from the heated surface. The key word there is away. The jets represent material escaping the comet, blown outward by the pressure of vaporization. They should point away from the sun because that's where the heating comes from. The sunny side gets hot, the ices there turn to gas, and physics does the rest. So when observers claim they're seeing jets pointing toward the sun, they're describing something that shouldn't happen according to our standard models. It would be like watching water flow uphill or smoke sink instead of rise. Not impossible in every context, but requiring special circumstances and demanding explanation. The speculative interpretation is seductive in its simplicity. What if these aren't passive outgassing jets at all? What if they're directed emissions, controlled, and purposeful? What if we're watching something adjust its trajectory using precisely aimed thrusters? Before you start composing your message to the Galactic Federation, let's pump the brakes for a moment. Probability arguments in science are tricky beasts. They seduce with their mathematical certainty, but they hide assumptions that can completely change the answer. Selection bias is a killer. If you observe 1,000 comets and find one with unusual jet alignment, is that remarkable? Or is it exactly what you'd expect from random variation across a large sample? If you look at enough objects, eventually you'll find some that cluster at the statistical extremes. That's not conspiracy. That's just how numbers work. Observation angles matter too. We're viewing 3I Atlas from Earth, which means we're looking at it from one specific vantage point as it moves through three-dimensional space. What appears to be pointing toward the sun, from our perspective, might actually be pointing somewhere else entirely, when you account for projection effects and geometry. Imagine watching a plane fly overhead and trying to determine its exact heading based solely on how it looks from the ground. You might think it's flying due north when it's actually heading northeast, simply because of your viewing angle. The same principle applies here, except the geometry is vastly more complex, and the stakes of getting it wrong are considerably higher. So what does peer-reviewed science actually say about 3I Atlas? Most researchers studying this object see it behaving fundamentally like a comet. NASA's observations confirm gas and dust outgassing consistent with solar heating. The coma, that fuzzy envelope of gas and dust surrounding the nucleus, shows the spectral signatures we expect from sublimating ices. The object brightens as it approaches the sun and dims as it recedes, exactly as a comet should. From this mainstream perspective, 3I Atlas is weird but not inexplicable. Unusual but not artificial. But there are real measured anomalies that even the skeptics can't dismiss. The polarization measurements, for instance, show extremely negative values not typically seen in solar system comets. Polarization tells us about the size and properties of dust grains in the coma. Negative polarization suggests particles with unusual optical properties, potentially indicating surface textures or compositions we don't commonly encounter. Is this proof of artificial origin? Absolutely not. Is it scientifically intriguing and worthy of intense study? Absolutely yes. Think about comet behavior this way. You're standing in your kitchen holding an ice cube on a hot summer day. As it melts, water drips down. The direction of those drips is determined by gravity and the shape of the ice. Now, imagine that ice cube is tumbling through space, heated unevenly by a distant star, made of multiple types of ice with different sublimation, temperatures, covered in dust that insulates some areas while exposing others. The pattern of outgassing becomes vastly more complex. Jets can appear to point in surprising directions based on the rotation of the nucleus, the distribution of volatile materials, and the geometry of surface features. What looks directed might simply be the natural consequence of a complex tumbling object responding to external heating in ways our simplified models struggle to predict. Statistics in science differ fundamentally from everyday interpretations. When someone tells you an event has 1 in 40,000 odds, your gut reaction is to think it couldn't possibly happen by chance. But scientists deal with massive datasets where low probability events become virtually guaranteed. Sequence the genomes of 1 million organisms and you'll find mutations with 1 in a million probabilities scattered throughout. That doesn't make each one miraculous. It makes them inevitable consequences of large sample sizes. The same principle might apply here. We're observing an interstellar object, something inherently unusual by definition. Should we really be surprised when it exhibits features that sit at the tail end of normal distribution curves? Researchers emphasizing caution aren't being killjoys or engaging in motivated reasoning to protect their worldview. They're applying the same standards that prevented us from declaring Oumuamua an alien probe when early observations showed anomalous acceleration. Further analysis revealed that acceleration could be explained by outgassing-induced thrust, a perfectly natural phenomenon. The unusual became explicable. The same process needs to happen here before we escalate from scientifically interesting to paradigm-shattering. So are we seeing physics we don't understand, or just an object that stretches our expectations? Maybe the answer is both. Maybe the truth lies not in artificial versus natural, but in recognizing that natural processes operating at the extremes of parameter space can produce outcomes that challenge our intuitions. Or maybe, just maybe, there's something here that won't fit neatly into our existing frameworks, no matter how hard we try to force it. 48 hours and counting. The data keeps coming in, and the debate rages on. Timing is everything in conspiracy theories. When two unusual events happen simultaneously, the human brain immediately starts drawing connections, spinning narratives, constructing explanations for why these things must be related. It's a survival instinct gone haywire in the information age. So when word leaked that the United Nations was conducting a planetary defense drill around the same time 3i Atlas makes its closest approach to Earth, the internet did what it does best. It lost its collective mind. Planetary defense drills are not new. They're routine international simulations designed to test how various nations and space agencies would coordinate their response to an actual Earth impact threat. Think of them as fire drills, but for civilization-ending asteroid strikes. The United Nations established the International Asteroid Warning Network specifically for this purpose. Multiple times per year, they run scenarios where participants role-play their way through detecting a threat, calculating its trajectory, deciding on intervention strategies, and coordinating global communications. It's boring bureaucratic stuff, honestly. Lots of PowerPoint presentations and working groups debating protocol. But the timing of this particular drill created an irresistible narrative. 3i Atlas approaches Earth. The UN suddenly decides now is the perfect moment for war games involving planetary threats. Surely these events must be connected, right? Surely the public statements claiming the drill was long scheduled and unrelated to any specific object are just cover stories meant to prevent panic, right? This is where correlation and causation have a nasty habit of getting tangled up in ways that make rational analysis nearly impossible. Let's establish some facts. 3i Atlas poses zero danger to Earth. Its closest approach, distance of 1.8 astronomical units, means it will pass us at roughly the same distance as a conversation between Mars and Earth when they're relatively near each other. There is no possibility of impact. None. The trajectory is well established, confirmed by multiple observations, and shows no indication of changing course. Any suggestion otherwise requires believing that every major observatory on Earth, plus multiple space-based telescopes, plus amateur astronomers tracking this object independently, are all either mistaken or complicit in some vast cover-up. The math just doesn't support impact scenarios, no matter how many YouTube videos claim otherwise. The UN drill, for its part, appears to be exactly what officials say it is: a pre-planned exercise that happens to overlap with an interesting astronomical event by pure coincidence. The International Asteroid Warning Network conducts these regularly. Check their published schedule from months ago, and you'll find references to exercises planned for this general time frame. The fact that 3i Atlas happens to be nearby is cosmically ironic, but procedurally irrelevant. Real threats aren't scheduled around drill calendars. So why does this explanation feel unsatisfying to so many people? because institutional messaging and public perception exist in different universes. When officials say, routine exercise, nothing to worry about, a certain percentage of the population hears, something is definitely wrong and they're hiding it from us. This isn't pure paranoia. Governments have hidden information before. Official reassurances have preceded disasters. The relationship between institutions and the public has been damaged by decades of selective transparency and revelations of past cover-ups. When trust is broken, even honest, communication gets filtered through suspicion. Social media amplifies this distrust exponentially. A single post suggesting the drill might be connected to 3i Atlas can reach millions within hours. Comment sections fill with people sharing similar suspicions, creating an echo chamber where speculation becomes reinforced as fact simply through repetition. Someone notes that major governments are participating. Another person points out increased military chatter on certain frequencies. A third mentions supply chain disruptions that might indicate preparations for something big. None of these data points actually connect to 3i Atlas in any meaningful way, but pattern-matching brains weave them into a coherent narrative regardless of actual causation. The psychology behind this phenomenon runs deeper than simple conspiracy thinking. Humans have always projected meaning onto cosmic events. Ancient civilizations saw comets as omens, usually bad ones. Wars, plagues, the deaths of kings, all attributed to those fuzzy lights moving against the fixed stars. We've learned to separate celestial mechanics from terrestrial disasters, but that ancient impulse to find meaning in the sky hasn't disappeared. It's just mutated into modern forms, trading divine wrath for government conspiracies and alien visitations. The amateur astronomy community provides an interesting counterpoint. These are people with genuine expertise, expensive equipment, and the skills to verify observations independently. Their reactions to 3i Atlas range from genuine scientific excitement about studying an interstellar object to bemused frustration at wild speculation, to cautious acknowledgement that some features don't fit standard models perfectly. This diversity of informed opinion suggests the truth lies somewhere in messy middle ground, not at either extreme of totally normal comet or definitely alien spacecraft. Media coverage reflects this spectrum. Reputable outlets emphasize the scientific opportunity while noting unusual features that merit investigation. Tabloids and click-driven sites hype danger and mystery, often stretching facts into speculation and presenting hypotheses as conclusions. And somewhere in between, people trying to understand what's actually happening struggle to separate signal from noise, fact from interpretation, data from narrative. The Cold War provides useful historical parallel. During nuclear test drills, populations were told everything was routine, even as governments genuinely prepared for potential apocalyptic scenarios. The drills were real preparation for real threats, but public communication downplayed fear to prevent panic and maintain social stability. Whether that approach was justified or patronizing remains debated. But it established a template where official calm and private concern could coexist, where nothing to worry about could mean both, we have this handled, and we don't want you to know how serious this might be. So are we in that situation now? Is the UN drill connected to 3i Atlas in ways officials won't acknowledge? Almost certainly not. The evidence points toward genuine coincidence, with the overlap creating narrative opportunities that speculation rushed to fill. But the mere fact that we're asking these questions reveals something important about how uncertainty breeds conspiracy thinking, how institutional messages fail to penetrate public distrust, and how cosmic events continue to trigger our deepest existential anxieties about what might be coming for us from the dark between the stars. What if? Those two words have launched 1,000 scientific breakthroughs and 10,000 baseless conspiracy theories. The difference between them often comes down to evidence, methodology, and the willingness to abandon attractive ideas when data contradicts them. So let's play the what-if game responsibly, exploring alternative interpretations of 3I Atlas while clearly labeling which ideas have scientific support and which exist solely in the realm of speculation. What if this object isn't passive debris at all? What if those jets we're observing aren't random outgassing from solar heating, but precisely controlled emissions designed to adjust trajectory and orientation? The idea of artificial propulsion in space isn't science fiction. We use it ourselves. Satellites and spacecraft make constant tiny adjustments using small thrusters, burning fuel to change velocity and direction. The physics is straightforward. Newton's third law. For every action, there's an equal and opposite reaction. Eject mass in one direction, and you move in the other. Could an advanced civilization build something that looks like a comet, but functions as a spacecraft? Here's where we need to separate what's theoretically possible from what's actually observed. Comets naturally create reactive forces through outgassing. As ices sublimate and gas escapes, the comet experiences a small push in the opposite direction. This isn't propulsion in the intentional sense, but it does create measurable acceleration. We've known this since the 1800s, when astronomers noticed comets deviating slightly from purely gravitational orbits. The phenomenon is called non-gravitational forces, and it's completely expected behavior for any icy body heated by a star. So the mere presence of forces that look like thrust doesn't immediately suggest artificial origin. It suggests we're looking at a comet doing what comets do, but the speculation doesn't stop there. Online forums have dissected 3I Atlas's composition, claiming unusual metal content, nickel and iron ratios that shouldn't exist in a natural object. Let's address this carefully. Some social media posts have indeed made these claims, often citing unnamed sources or misinterpreted data. However, verified spectroscopy from professional observatories shows primarily ices and typical cometary volatiles, carbon dioxide, water ice, organic compounds. The spectral signatures match what we'd expect from an interstellar visitor that formed in a molecular cloud around a young star somewhere across the galaxy. Are there trace metals? Probably. Comets aren't pure ice. They contain rocky and metallic components mixed throughout, but unusual metal ratios that suggest artificial construction? That claim hasn't appeared in peer-reviewed literature for 3I Atlas. The James Webb Space Telescope has provided the most detailed compositional analysis yet. Its infrared observations reveal a coma dominated by carbon dioxide, which is actually quite rare for comets in our solar system, but perfectly consistent with interstellar chemistry. Objects forming in the cold outer regions of distant planetary systems might trap more carbon dioxide than water ice, depending on local conditions when they formed billions of years ago. This makes 3I Atlas chemically interesting, but not chemically impossible. Different origin environments produce different outcomes. That's not mystery. That's just chemistry responding to initial conditions. Then, there's the trajectory argument. 3I Atlas passed relatively near Jupiter before approaching Earth. Some speculative sources suggest this proximity couldn't be coincidental, that the object must be targeting Jupiter's gravity well for some purpose, perhaps using it for a gravitational assist or as a waypoint in a planned route through our solar system. This sounds compelling until you understand orbital mechanics. Jupiter is massive. Its gravitational influence dominates the outer solar system. Any object entering from interstellar space has a high probability of having its trajectory bent by Jupiter's gravity. That's not targeting. That's just physics. Throw a ball into a room with a powerful magnet and it will curve toward the magnet. That doesn't mean the ball was aimed at it. Historical parallels help here. Remember Oumuamua? When astronomers detected its unusual acceleration, some researchers, including reputable scientists from major institutions, suggested it might be artificial. A light sail, perhaps, pushed by radiation pressure. or a defunct probe from another civilization tumbling through space. These weren't fringe ideas. They appeared in scientific papers and sparked genuine academic debate. Eventually, more mundane explanations involving hydrogen outgassing gained acceptance, though controversy persists. The point is that science has mechanisms for handling these questions. Propose hypothesis, test against data, update understanding. The process works even when the initial speculation sounds wild. The human brain excels at detecting agency. Our ancestors survived because they could distinguish between wind-rustling bushes and predators stalking through undergrowth. Better to mistake the wind for a threat than to mistake a threat for wind. That cognitive bias persists. We see faces in clouds and patterns in randomness. We attribute intention to events that might be purely mechanistic. This doesn't make us foolish. It makes us human. But it does mean we need to be extra careful when evaluating evidence for intelligence in ambiguous situations. So, let's look at specific fringe hypotheses circulating online, clearly labeled as community speculation rather than scientific consensus. Some Reddit threads suggest 3i Atlas contains hidden internal structures, perhaps a central core surrounded by ice camouflage. Others propose it might be a probe that's been dormant for millions of years, activated by proximity to our sun. A few suggest it could be a warning beacon, or even a weapon system from an extinct civilization. These ideas range from creative to absurd, but they share a common thread. They attribute agency and purpose to an object that might simply be an unusual rock with ice on it, traveling through space, because that's what debris does when gravitational interactions eject it from planetary systems. Natural explanations can absolutely be weird without being artificial. Nature is creative. Billions of years and countless star systems mean we should expect to encounter objects at the extremes of physical parameter space. The question isn't whether 3i Atlas is strange. It clearly is. The question is whether that strangeness requires extraordinary explanations or merely challenges our limited experience with interstellar visitors. When you've only seen 3 of something in all of human history, maybe the third one looking different doesn't mean conspiracy. Maybe it just means small sample size and selection effects. The universe is big and weird and surprising. Sometimes a strange comet is just a strange comet, even when every instinct screams that there must be more to the story. There's a particular kind of momentum that builds when anomalies start piling up. One weird thing is curious. 2 weird things are interesting. 3 or more weird things happening simultaneously. And suddenly, you're in pattern recognition territory, where the human brain starts connecting dots, whether or not those connections actually exist in reality. 3i Atlas presents us with exactly this situation. Multiple unusual features, each potentially explicable on its own, but collectively creating a profile that refuses to fit comfortably into our expectations. So, let's systematically walk through what's actually been observed and separate real measurements from interpretive spin. The anti-tail pointing toward the sun remains the most visually striking feature. Traditional comet tails stream behind the nucleus, blown backward by solar wind and radiation pressure. But telescopic observations have documented a tail structure extending in the sun's direction. Before we jump to conclusions about physics-defying behavior, let's understand what might create this appearance. Anti-tails have been observed in solar system comets before, particularly when viewing. Geometry creates projection effects that make dust trails appear to point sunward. Think of it like watching a contrail from an airplane. From certain angles, that trail can appear to point toward or away from the horizon in ways that seem wrong until you account for 3-dimensional perspective, compressed into 2-dimensional observation. Dust particles moving away from a comet don't all travel at the same speed or in exactly the same direction. Larger particles move more slowly and get left behind in the comet's orbital path. When Earth passes through that orbital plane at specific angles, we might observe older dust that appears to lead the comet rather than trail it. This isn't the dust pointing toward the sun. It's older material from previous outgassing events that happens to lie between us and the sun from our viewing position. The comet itself continues moving normally, but the geometry creates an optical illusion that looks like an anti-tail. Now, is this definitely what's happening with 3I Atlas? The analysis isn't complete yet. Some researchers remain puzzled by features that don't match standard anti-tail models perfectly. But the existence of a potential conventional explanation means we can't immediately declare the observation impossible or unnatural. We need more data, better viewing angles, and detailed modeling before concluding that physics has gone haywire. The polarization anomaly presents a different kind of puzzle. When sunlight scatters off particles in a comet's coma, that light becomes polarized in predictable ways depending on particle size, shape, and composition. Most comets show positive polarization at certain viewing angles. 3I Atlas shows extremely negative polarization, more negative than any solar system comet measured to date. This tells astronomers something unusual about the dust grains surrounding the nucleus. Perhaps they're especially small. Perhaps they have unusual surface textures. Perhaps their composition includes materials that scatter light differently than typical silicates and organics. Is this proof of artificial origin? Not even close. It's proof that 3I Atlas contains dust particles with optical properties we don't commonly encounter. That could mean it formed in a different chemical environment than our solar system comets. Interstellar space differs from our local neighborhood. Temperature, radiation background, chemical abundances, all these factors vary across the galaxy. An object born around a different star, perhaps a star of different mass and composition than our sun, might naturally contain materials that behave oddly when we shine light on them. Unusual doesn't equal impossible. It equals interesting. Brightness variations add another layer. 3I Atlas has shown rapid brightening events, moments where its apparent magnitude increases dramatically over short timescales. Comets do brighten as they approach the sun, that's expected, but the specific pattern of brightening observed here shows spikes and variations that suggest either complex surface activity or rotational effects where different regions with different volatile content get heated as the nucleus tumbles. Some observers see this complexity and think intentional signaling. Scientists see it and think heterogeneous nucleus with localized active regions. Color changes have been noted as well. The coma's color isn't uniform across all wavelengths, and it shifts over time. Again, perfectly normal for comets, where different molecules emit light at different wavelengths, and their relative abundances change as various ices sublimate at different rates depending on temperature. Carbon dioxide sublimates at colder temperatures than water ice. As the comet moves closer to the sun, the mix of gases changes, and the observed color shifts accordingly. What looks like intentional display is just chemistry following thermodynamic gradients. The trajectory itself invites speculation. 3I Atlas entered our solar system from interstellar space, past Jupiter, and will approach Earth before heading back out into the cosmic void. Some claim this path is too convenient, too specifically targeted to be random wandering, but orbital mechanics is deterministic. Give me an object's position, velocity, and the gravitational field it's moving through, and I can calculate its path precisely. The trajectory of 3I Atlas is entirely consistent with gravitational dynamics. It didn't need to aim. Gravity aimed it the same way a river channels water downhill without the water needing intentions. Online communities have constructed elaborate narratives connecting all these features into grand unified theories of artificial origin. Every observation becomes evidence. Every ambiguity gets interpreted in the direction of mystery, rather than toward mundane explanation. This is where science and storytelling diverge. Science says explain each anomaly with the simplest hypothesis consistent with known physics, then see if those simple explanations collectively account for the observations. Storytelling says find the one dramatic explanation that makes sense of everything at once, even if that explanation requires new physics or the existence of entities we've never detected before. The mirage analogy works well here. Imagine seeing a pool of water on a desert road ahead. It looks real. It shimmers and reflects light exactly as water should. But as you approach, the water recedes and eventually disappears because it was never there. Light bending through, temperature gradients created an illusion that looked like something it wasn't. Understanding the optics doesn't make the mirage less visually convincing. It just explains why your interpretation was wrong. We might be looking at something similar with 3i Atlas, a collection of real observations that create the appearance of something impossible when viewed through incomplete understanding and unfavorable geometry, but that resolve into normal behavior once we account for all the relevant factors. Modern tools are changing how we detect and analyze anomalies. Artificial intelligence can process enormous datasets, identifying patterns human observers might miss or correlations that emerge only when you look at millions of measurements simultaneously. This power cuts both ways. AI might reveal genuine features that confirm conventional comet behavior in exquisite detail, or it might highlight clusters of oddness that demand new explanations. The key is maintaining epistemic humility. Science thrives on anomaly. Finding things that don't fit forces us to refine models and expand understanding, but not every anomaly overturns paradigms. Most just refine them. The challenge is knowing which is which before history renders its verdict. Cast your mind back a few centuries. Astronomy meant long nights in cold observatories, squinting through eyepieces, sketching positions of stars and planets by hand, measuring angular separations with mechanical instruments, and hoping clouds didn't ruin months of careful work. The human eye was the detector. The human brain was the processor. And the rate of discovery was limited by how many hours a person could stay awake and how many objects they could catalog before exhaustion or death ended their contribution to science. Fast forward to today. Automated telescopes scan the entire sky repeatedly, recording millions of observations per night. Digital cameras capture photons with precision no human retina could match. Computer algorithms sift through this avalanche of data, identifying moving objects, unusual brightening, spectral anomalies, anything that deviates from expected patterns. And increasingly, artificial intelligence joins the process, bringing pattern recognition capabilities that transform how we understand the cosmos. Recent breakthroughs in AI-driven astronomy have been genuinely remarkable. Machine learning algorithms trained on existing asteroid and comet catalogs can now identify new objects with stunning efficiency. In the past year alone, AI systems have flagged over 1 million previously unknown asteroids in archival data, bodies that human astronomers simply didn't have time to spot and characterize. These aren't trivial discoveries. Some of those asteroids pass near Earth. Others occupy unusual orbits that tell us about the solar system's formation. A few might even be targets for future spacecraft missions, or eventually, resource extraction. The way this works is elegantly simple in concept, brutally complex in execution. You feed the AI thousands of examples of known asteroids in telescope images. The algorithm learns to recognize the characteristic patterns, the slight movement against background stars, the way real objects differ from noise or cosmic rays or instrumental artifacts. Once trained, the AI can process new images far faster than humans, flagging candidates for follow-up observation. It's like having a tireless assistant who never gets bored checking every frame for tiny dots that might be something interesting. But asteroid detection is just the beginning. AI excels at finding subtle patterns in noisy data. This makes it perfect for analyzing comet behavior. Consider 3I Atlas. Multiple telescopes are observing it, generating spectroscopic data about its chemical composition, photometric measurements tracking its brightness, astrometric data recording its position over time. That's already more information than any single astronomer could reasonably process by hand. Now, multiply that by hundreds of other observed comets, and you start to see the problem. There's just too much data for traditional analysis methods. Enter machine learning. An AI system can compare 3I Atlas against every other comet ever observed, identifying which features are truly unusual versus which just seem odd because of our limited human perspective. It can model dust particle distributions in the coma, predict expected polarization patterns, and highlight discrepancies that warrant deeper investigation. It can even suggest observation strategies, recommending specific wavelengths or viewing angles most likely to resolve ambiguities. Think of it as a cosmic detective's assistant, one that never sleeps and has perfect memory of every case ever solved. There's a particularly compelling recent example that demonstrates this technology's potential. Researchers used AI to analyze light curves from tens of thousands of variable stars, finding unusual periodic dimming patterns that suggested previously unknown eclipsing binaries and even potential exoplanet transits that earlier searches had missed. The algorithm didn't just confirm what humans already suspected, it revealed entirely new phenomena hiding in plain sight within data we thought we'd already fully exploited. That's the promise here. AI doesn't just work faster, it sees differently. So how might this apply to understanding 3I Atlas? Imagine an AI system trained on all known comet observations, including Oumuamua and Borisov. It could assess whether the claimed anomalies are statistically significant or within expected variation for interstellar visitors. It could model jet behavior under different assumptions about nucleus composition, rotation, and active regions, then compare predicted observations against actual data to see which models fit best. It could even evaluate the famous 14th anomaly, running millions of simulations of random jet orientations to precisely calculate how unlikely the observed configuration actually is. The limitations matter too. AI systems are only as good as their training data. If we've never observed something before, the algorithm might classify it incorrectly simply because it lacks context. Machine learning can also inherit human biases embedded in the training sets. If we mostly studied comets from our own solar system, an AI might flag all interstellar visitors as anomalous simply because they're different, not because they're impossible. Human supervision remains critical. The AI suggests, humans decide, but there's another angle worth considering. Future interstellar visitors will benefit enormously from these advances. Early detection is key. The sooner we spot an incoming object, the more time we have to observe it across different wavelengths and viewing geometries. AI-powered surveys like the upcoming Legacy Survey of Space and Time will monitor the entire visible sky continuously, catching transient events and moving objects that previous surveys would have missed. When the next Oumuamua or 3I Atlas enters our solar system, we might detect it months or even years earlier than we would have with traditional methods. Better composition modeling follows from better detection. If we can track an interstellar visitor throughout its entire pass through the inner solar system, we can watch how its activity changes with solar distance, which volatiles sublimate at which temperatures, how the coma structure evolves. That's data gold. It lets us test formation theories and understand what conditions existed in the planetary system where the object originated. Every interstellar visitor is a message in a bottle from another part of the galaxy, carrying chemical information about environments we can't yet visit. AI helps us read those messages more clearly. There's even speculation about using AI for anomaly detection in the other direction, not finding natural objects that look unusual, but identifying potential signatures of technology. If an interstellar visitor really were artificial, what patterns would betray its origin? regular geometric structures, spectral lines from refined metals, or unusual isotope ratios. Trajectory changes inconsistent with purely gravitational or outgassing effects. An AI trained on the distinction between natural phenomena and human-made spacecraft might notice subtle signatures that human observers would rationalize away as observation errors or instrumental artifacts. Other applications in 2025 have shown AI's astronomical potential. Surveys have used machine learning to classify galaxy morphologies, identify gravitational lenses, detect faint tidal streams around galaxies, and even predict stellar evolution outcomes. Each application reveals patterns at scales or sensitivities impossible for human analysis alone. The cosmos is more complex and more surprising than our models anticipated. AI is helping us navigate that complexity without drowning in detail. As we count down to 3I Atlas's closest approach, these tools stand ready. Whatever we observe in the next 48 hours will be processed, analyzed, and interpreted with technological sophistication that would have seemed like magic just a generation ago. Whether this reveals a strange but natural comet or something that demands paradigm revision, we'll know with greater certainty than ever before. The universe is complex. Our tools for understanding it grow stronger each year. And maybe that's the real story here. Not whether this particular object is natural or artificial, but that we've reached a point where we can actually answer that question rigorously instead of just guessing based on insufficient data and hopeful thinking. Science doesn't exist in a vacuum. While astronomers track 3I Atlas and debate its nature, other researchers are achieving breakthroughs that might seem unrelated, but actually reshape our entire approach to understanding and exploring space. 2025 has been a remarkable year for fundamental physics and engineering, and two developments in particular deserve attention as we think about what comes next, not just for this object, but for humanity's relationship with the cosmos. Nuclear fusion research hit a major milestone this year. For decades, scientists have chased the dream of controlled fusion energy, attempting to recreate on Earth the process that powers stars. The challenge is brutal. You need to heat hydrogen isotopes to tens of millions of degrees, confine that plasma long enough for nuclei to overcome their mutual electrical repulsion and fuse, and extract more energy from the reaction than you put in to start it. It's harder than it sounds. It's actually harder than most things that have ever been attempted. But recent experiments at major fusion facilities have achieved sustained energy gain. Not just a brief spike where output exceeded input for microseconds, but maintained fusion reactions that produced significantly more power than the lasers or magnetic fields required to initiate them. This is the kind of breakthrough that appears in textbooks. Future engineers will study these experiments the way we studied the Wright brothers' first flight or the Manhattan Project. It represents crossing a threshold from maybe possible someday to definitely achievable with refinement. Why does this matter for space exploration? Everything comes back to energy. Moving through space requires pushing mass. Faster travel requires pushing more mass or pushing it faster, both of which demand enormous energy. Chemical rockets have taken us to the moon and sent probes throughout the solar system, but they're fundamentally limited by how much energy can be extracted from chemical bonds. Nuclear fission offered improvement, but came with radiation concerns and limited fuel energy density. Fusion promises something different. Energy yields thousands of times greater than chemical reactions. Fuel sources that could be extracted from planetary atmospheres or water ice. The potential to drastically reduce transit times to distant destinations. Imagine a fusion-powered spacecraft visiting an interstellar object like 3I Atlas. Instead of passive observation from Earth distance, we could send a probe that matches its velocity, travels alongside it, deploys landers to its surface. We could analyze its composition directly instead of inferring chemistry from spectral lines. We could measure its mass, map its interior structure with ground-penetrating radar, confirm or rule out any internal cavities that might suggest artificial construction. The difference between remote sensing and in situ exploration is the difference between looking at a photograph of food and actually tasting it. The second breakthrough involves quantum computing in space. Earlier this year, researchers successfully operated a quantum processor aboard a satellite platform, demonstrating that delicate quantum states can be maintained even in the harsh environment of orbit. This might sound esoteric, but quantum computers excel at specific types of calculations that classical computers struggle with, including optimization problems and simulations of quantum systems. For space applications, this opens fascinating possibilities. Quantum sensors could detect minute variations in gravitational fields, potentially mapping the interior structure of asteroids or planets with precision impossible using classical techniques. Quantum communication systems promise unhackable data transmission, critical for coordinating spacecraft across vast distances. And quantum computers might help us model complex chemical reactions in cometary comas, or optimize trajectory calculations for missions requiring multiple gravitational assists. Think about how this could apply to analyzing objects like 3I Atlas. The spectroscopic data we're collecting contains information about molecular transitions in excited gas states, quantum mechanical processes happening in real time as solar radiation interacts with cometary material. Classical computers can model these processes, but only approximately and at great computational cost. Quantum computers could simulate the actual quantum mechanics directly, potentially revealing subtle features in the spectral data that classical analysis misses. Maybe those unusual polarization measurements would make more sense if we could model the quantum scattering processes at the microscopic level. There's also the question of what these technologies enable for future detection. Better instruments mean earlier warning when interstellar visitors enter our solar system. Quantum sensors might spot minute light variations or gravitational perturbations years before traditional telescopes notice anything unusual. Fusion propulsion could launch quick-response missions to intercept and study these objects before they vanish back into the cosmic dark. Instead of passive observation during a brief window, we could actively investigate with sophisticated equipment on site. But the broader implication here involves mindset. When people ask whether 3I Atlas might be artificial, they're really asking whether we're alone in a universe full of dead matter, or whether intelligence might have touched this object at some point in its journey. The question feels overwhelming, because the implications of either answer reshape everything. But maybe we're thinking about it wrong. Maybe the relevant question isn't about this specific object, but about developing capabilities that let us answer such questions definitively instead of endlessly speculating. If we had fusion propulsion and quantum sensors and AI-driven analysis, we wouldn't need to debate whether unusual jet alignment suggests propulsion or just weird geometry. We'd send a probe to check directly. If we had the technological sophistication to intercept interstellar visitors routinely, the mystery would evaporate. We'd build a catalog of normal interstellar objects, establish what range of features occurs naturally, and immediately recognize anything that falls outside those bounds. Speculation would give way to measurement. Debate would yield to data. This represents a fundamental shift in humanity's relationship with these questions. For all of history until now, we've been passive observers of the cosmos, limited to watching whatever happens to pass nearby and hoping our instruments are good enough to tell us something useful. But we're transitioning toward active exploration, where we choose what to investigate and bring tools sufficient for decisive conclusions. That transition is happening now, powered by breakthroughs in fusion, quantum computing, AI, and countless other fields that seem disconnected until you realize they're all building toward the same future. So as we watch 3I Atlas make its closest approach, Count down those final hours until December 19th. We should hold two thoughts simultaneously. First, this object is a genuine mystery with features that challenge conventional explanation and deserve rigorous investigation. Second, regardless of what it turns out to be, our capacity to investigate the next such object will be vastly greater than our capacity to investigate this one. The tools are coming online. The technology is maturing. The future where we definitively answer whether we're alone is approaching faster than most people realize. Whether those jets are outgassing or thrusters, whether that trajectory is chance or intention, whether we're looking at ancient ice or something that once carried purpose across the stars, the fact that we're asking these questions with increasingly sophisticated tools is itself the story. Curiosity drives exploration. Exploration drives discovery. Discovery drives technology. And technology enables us to satisfy the curiosity that started the whole cycle. Round and round it goes, spiraling upward toward capabilities our ancestors couldn't imagine and our descendants will take for granted. 3i Atlas is one data point in that progression. A strange one, certainly. A controversial one, absolutely. But ultimately, just one step in a much longer journey toward understanding what else is out there in the cosmic dark, and whether any of it is looking back at us with recognition and intent, or whether we remain alone in a universe magnificent and terrifying in its indifference.